Welcome to our deep dive into propositional logic and set theory. In this chapter, we'll explore the essential concepts that form the backbone of mathematical reasoning. By the end, you'll understand how to distinguish between statements and sentences, evaluate truth values, use logical connectives, and apply set operations. We'll also cover how to represent sets visually with Venn diagrams and introduce you to the world of quantifiers and argument. Whether you're new to these ideas or looking to strengthen your foundation, this journey will equip you with the tools needed for advanced mathematical thinking. Let's get started by laying out the main objectives and why these topics matter. Mathematical logic is the language of reasoning. It helps us make sense of statements, arguments, and proofs. The roots of modern logic trace back to George Boole in the 19th century, and since then it has become a vital part of deductive science. Understanding logic isn't just for mathematicians, it's a skill that sharpens critical thinking in everyday life. In this chapter, we'll start with the basics of propositional logic, which focuses on the logic of sentences and their truth value. Let's see how logic forms the foundation for all mathematical arguments. Not every sentence is a statement in logic. In propositional logic, we focus on declarative sentences, those that can be clearly labeled as true or false. For example, Addis Ababa is the capital of Ethiopia is a statement even if we don't know its truth value. On the other hand, commands like stop writing are not statements because they can't be assigned a truth value. Understanding this distinction is crucial as we move forward, since only statements can be analyzed logically. Next, we'll see how to identify propositions and their truth values. Proposition is a sentence that has a definite truth value, either true or false. It doesn't matter if we know the truth value or not, what matters is that one exists. For example, 3 is less than 10 is a proposition and it's true. Emperor Tewodros weighed 30 kgs on his 10th birthday is also a proposition, even if we can't verify it. This concept is foundational because all logical analysis starts with proposition. Next, we'll practice identifying which sentences are propositions and which are not. Let's look at some examples to clarify what counts as a proposition. Ethiopia is in Asia is a proposition even though it's false. May God bless you is not a proposition because it's a wish, not a statement. Mullah Zanwi was Ethiopian prime minister is a proposition, and so is Munas Tu plus 6x4. The key is whether the sentence can be assigned a truth value. This skill is essential for analyzing logical arguments and constructing valid proof. Now, let's explore how we combine propositions using logical connectives. Logical connectives are words like and, or, and implies that let us combine propositions into more complex statements. For example, Ethiopia is in Africa and Kenya is in Europe joins two propositions with and. The truth value of the combined statement depends on the truth of its parts and the connective used. We use symbols like and, or, and implies to represent these connections. Understanding how these connectives work is crucial for building and analyzing logical arguments. Let's break down each connective and see how they function. Conjunction, represented by and, combines two propositions and is true only if both parts are true. For example, if P is 3 is greater than 2 and Q is 4 is greater than 3, then PQ is true only if both P and Q are true. If either is false, the whole conjunction is false. This rule is best illustrated with a truth table, which shows all possible combinations of truth values. Mastering conjunctions helps you understand how complex statements are built from simpler ones. Disjunction, represented by or, is true if at least one of the propositions is true. In logic, or is inclusive, meaning both parts can be true at the same time. For instance, if P is true and Q is false, PQ is still true. This differs from everyday language where or can sometimes mean only one or the other. Understanding this distinction is important for interpreting logical statements correctly. Let's look at the truth table for disjunction to see how it works in all cases. Implication, written as if P then Q, PQ is a key logical connective in mathematics. It's true in all cases except when P is true and Q is false. For example, if every equilateral triangle is equiangular, then every equilateral triangle is isosceles is an implication. Even if the premise seems unrelated or false, the implication can still be true according to the rules. This sometimes leads to counterintuitive results, but it's essential for formal reasoning and proofs. Implication, or logical equivalence, is written as P if and only if Q, PQ. This connective is true when both P and Q have the same truth value, either both true or both false. For example, all even numbers are divisible by 2 and all numbers divisible by 2 or even can be connected with a by implication. Understanding by implication is crucial for defining when two statements are logically equivalent, which is a common goal in proofs. Negation is a unique connective that acts on a single proposition. Written as not P, not sign P, it simply reverses the truth value. If P is true, not sign P is false, and vice versa. Negation is essential for expressing the opposite of a statement and for constructing more complex logical expressions. It's also a building block for many logical laws such as De Morgan's laws, which we'll encounter later. Let's see how negation works in practice. When we combine multiple propositions using logical connectives, we create compound propositions. These can involve any combination of and, or, implies, and so on. For example, PQRS is a compound proposition. The truth value of a compound proposition is determined by systematically applying the rules for each connective. It's important to use parentheses to clarify the order of operations, just like in arithmetic. Let's practice evaluating compound propositions step by step. Determine the truth value of a compound proposition. Start by evaluating the innermost expressions and work outward. For example, if P is true, Q is false, R is true, and S is false, then PQ is false, RS is true, and PQRS is true. This process relies on the truth tables for each connective. Practicing these evaluations builds your skill in logical analysis and prepares you for more advanced topics like proofs and argument validity. Just like arithmetic, logic has rules for the order in which connectives are applied. Generally, conjunction and disjunction are evaluated before implication and by implication. Parentheses are used to clarify which operations come first. For example, PQR means PQR, not PQR. Keeping these conventions in mind ensures that your logical expressions are interpreted correctly and avoids ambiguity. Two compound propositions are equivalent if they have the same truth value for all possible combinations of their components. For example, PQ and NetSunPQ are equivalent, as shown by their identical truth tables. We use the symbol identical to denote equivalence. Recognizing equivalent propositions is important for simplifying logical expressions and constructing valid arguments. Let's see how to test for equivalence using truth table. In a conditional statement PQ, there are related forms: the converse QP, the inverse not sign P not sign Q, and the contrapositive not sign Q not sign P. Importantly, PQ is logically equivalent to its contrapositive, but not to its converse or inverse. Understanding these relationships helps you analyze and construct logical arguments more effectively. Let's look at examples to see how these variations work in practice. Logic is governed by several important properties, such as commutativity, associativity, distributivity, and De Morgan's laws. For example, PQ identical to QP commutative, and not sign PQ identical to not sign P not sign Q De Morgan's law. These properties allow us to manipulate and simplify logical expressions systematically. Mastering these laws is essential for constructing proofs and understanding the structure of logical argument. Tautology is a compound proposition that is always true, no matter what truth values its components have. For example, PP is a tautology. On the other hand, a contradiction is always false, such as P not sign P. Recognizing tautologies and contradictions is important for evaluating the validity of arguments and simplifying logical statements. Let's see how to identify these special cases using truth table. Open proposition is a sentence containing one or more variables, such as x is greater than 4. It becomes a proposition only when the variables are replaced with specific values. The set of possible replacements is called the universal set. Open propositions are the building blocks for more complex logical statements involving quantifiers, which we'll explore next. We often use letters like x, y, or z as placeholders in open propositions. For example, px might represent is a square root of 4. When we substitute a specific value such as p2, we get 2 as a square root of 4, which is a proposition. This notation helps us generalize statements and prepare for the use of quantifiers. Just like with regular propositions, we can combine open propositions using logical connectives. For example, PX, KX means x has both properties p and q. These compound open propositions are essential for expressing more complex mathematical ideas, especially when we introduce quantifiers like for all and there exists. Open propositions q, x, and r, x are equivalent if for every value in the universal set they have the same truth value. For example, px, x2 1 equals 0 and qx, x greater or equal to 1 are equivalent over the set -1 0 1. This concept is crucial for understanding how different logical expressions can represent the same mathematical idea. Quantifiers allow us to make statements about all or some members of a set. The universal quantifier x means for all x, while the existential quantifier x means there exists an x. For example, xpx asserts that every in the universe has property p, while xpx asserts that at least one x does. Quantifiers are fundamental for expressing general mathematical truth. To determine the truth value of a quantified statement, we check whether the property holds for all or some members of the universe. For example, x2 greater or equal to 0 is true for all real numbers, while x2 equals -1 is false for real numbers. Understanding how to evaluate quantified statements is essential for mathematical reasoning and proof. Gating quantified statements follows specific rules. The negation of xpx is x not sign px, and the negation of xpx is x not sign px. For example, the negation of all x are positive is there exists an x that is not positive. Mastering these rules is key for constructing correct logical arguments and proofs. You can combine quantified propositions using logical connectives just like with simple propositions. For example, xpx, xqx means p holds for all x and q holds for at least one x. Understanding how to build and interpret these compound statements is vital for advanced mathematical logic. Order of quantifiers matters. For example, xypxy means for every x there is a y such that pxy holds, while yxpxy means there is a y such that for every x pxy holds. These statements can have very different meanings and truth values. Always pay close attention to the order when interpreting or constructing quantified statements. Argument consists of premises and a conclusion. It is valid if, whenever all the premises are true, the conclusion must also be true. Validity depends on the logical form, not the content. For example, if P is true and PQ is true, then Q must be true. Understanding validity is essential for constructing sound mathematical proofs and reasoning. One way to test the validity of an argument is by using truth tables. List all possible truth values for the premises and conclusion. If in every case where the premises are true, the conclusion is also true, the argument is valid. This method is systematic and reliable, especially for arguments involving a small number of propositions. As arguments become more complex, truth tables can become unwieldy. Instead, we use formal proofs, which are sequences of statements justified by rules of inference. These rules, like modus ponens and modus tollens, allow us to derive conclusions step by step from the premises. Mastering these rules is crucial for constructing rigorous mathematical proofs. Some of the most important inference rules include modus ponens if p, q, and p, then q, modus tollens if p, q, and not sign q, then not sign p, and the principle of syllogism if p, q, and q are, then p are. These rules form the backbone of logical deduction and are used in almost every mathematical proof. Rules of replacement allow us to substitute logically equivalent expressions within a proof. Examples include De Morgan's laws, commutative and associative laws, and the contrapositive. Using these rules, we can simplify complex logical statements and make proofs more manageable. They are essential tools for anyone working with formal logic. Set theory is the study of collections of objects called sets. Sets are fundamental to all areas of mathematics. A set is a well-defined collection of elements, and we use capital letters to denote sets and lowercase letters for elements. Understanding sets and their properties is essential for everything from algebra to advanced mathematics. There are several ways to describe sets: verbally by listing all elements, roster method by partial listing with ellipses, and by set builder notation. For example, the set of vowels can be written as a E, I, O, U, or as X is a vowel in the English alphabet. Each method has its advantages depending on the context and the size of the set. Set A is a subset of B if every element of A is also in B. Written as a B, two sets are equal if they have exactly the same elements. The empty set, denoted by, is a subset of every set. Understanding these relationships is key for working with sets and proving set identities. The power set of a set A, denoted 2A, is the set of all subsets of A. For example, if A equals a B, then the power set is a B. Power sets are important in many areas of mathematics, including probability and combinatorics. The union of two sets A and B, written a B, is the set of all elements that are in A, in B, or in both. Union is commutative and associative, just like logical OR. Understanding union is essential for combining sets and analyzing their relationships. The intersection of two sets A and B, written a B, is the set of all elements that are in both A and B. Intersection is also commutative and associative, similar to logical AND. Mastering intersection helps you find common elements and analyze set relationships. The difference of two sets A and B, written a B, is the set of elements in A but not in B. The complement of a set A, written a, is the set of all elements not in A, relative to a universal set U. These operations are essential for expressing exclusion and negation in set theory. Venn diagrams are visual tools for representing sets and their relationships. Sets are shown as circles within a rectangle representing the universal set. Overlapping areas show intersections, while non-overlapping areas show differences. Venn diagrams make it easier to understand and solve problems involving unions, intersections, and complements. Let's look at some examples. If U is the set of one-digit numbers and A is the set of even numbers, we can use a Venn diagram to show A, its complement, and intersections with other sets. Venn diagrams help visualize set operations and make abstract concepts more concrete. Venn diagrams can also illustrate more complex set operations such as a B, A, and a \B. By shading different regions, we can represent unions, intersections, and differences visually. This makes it easier to solve problems and understand set relationships at a glance. Set theory has its own set of laws such as distributive, associative, and De Morgan's laws. For example, AB equals AB and a B equals AB. These identities are essential for simplifying set expressions and solving problems efficiently. The universal set U contains all elements under consideration. The complement of a set A, denoted A, consists of all elements in U that are not in A. Understanding the universal set and complements is crucial for working with set operations and Venn diagrams. Now that we've built a strong foundation in logic and set theory, we're ready to explore the real and complex number systems. Understanding numbers and their properties is essential for all areas of mathematics. In the next chapter, we'll define natural numbers, explore their operations, and see how these concepts connect to everything we've learned so far.